Hello, online participants, can you hear me? Hello.
Okay, that will be switched on automatically, I guess, right? That will be switched on. Yeah. Okay, so let me start anyway. So one point I perhaps should emphasize, the last time I said that even though the 13.6 electron volt, right, that number suggests that you have to go to very small lambda before the universe was ionized, right? Because like we got the number like 10 to the minus 5. That's where it was about 25 electron volts. The reason that if you think from the expansion of the universe, right? As the universe is cooling, one might have expected that once you go below 13.6 electron volt, once the temperature falls below, the protons and electrons would have combined. Okay. But what happens is that the electron density is much smaller than the photon density in the universe. That one can calculate because and one finds that the number ratio is about 10 to the 9. So now think of a proton, right? In order for it to form a hydrogen atom, it has to find an electron, right? And because the electron density is so small, that's a difficult job. After you have formed a hydrogen atom, suppose it has found an electron and formed a hydrogen atom. Then of course, there are many photons, right? 10 to the 9 photons, so it will get hit. But at a temperature below 13.6, most of these photons will not have enough energy to excite the electron, right? Because that's the definition of a temperature, right? At 13.6 electron volt, the average energy is 13.6 electron volt, right? But because the number is 10 to the 9, right? Even if most of the photons have energy lower than 13.6, there is always a fraction which have energy higher than 13.6, because that's the distribution, right? I mean, it's not that everything carries the same energy, right? There is a whole distribution. And so what one finds is that the probability that a hydrogen atom will get ionized, okay, is much more from the proton's perspective, right? It's much more than the fact that the probability that a hydrogen atom will form if it was starting from proton electron system. Okay. So this you can do, I mean, one has to do a more detailed calculation, right? But what one finds, even just equilibrium statistical mechanics, okay, tells us that the temperature is around 1000. So the lambda is about 1000. But one can do a little more detailed analysis, okay, to figure out exactly what the value of lambda is, and that takes into account non-equilibrium phenomenon, because it's a time-dependent process, right? The universe is expanding, so it's not that everything equilibrates at the same time. So that changes the value of lambda a little bit, right? But just from equilibrium statistical mechanics, you can make this conclusion that lambda is on the ballpark of 1000, and not not 1000. 1 over lambda, the redshift is of the order of 1000, and not 10 to the 5, right? Which just naive energy calculation will indicate that it's 10 to the 5. Exactly. I mean, it's basically the fact that the number of photons is much more than the number of electrons, right? So chance of colliding with an electron is much less than the chance of colliding with a photon, right? So given everything else equal, right, it's much more likely that the once you form a proton, once you form a hydrogen atom, it will just get ionized. Yeah, so there's a balance, right? Once the temperature falls sufficiently below, then even if the 10 to the 9 doesn't win, right? Because the Boltzmann suppression factor kills you, and you find that it's not that the fraction of photons that carry that much energy still is very small, right? And that's where the things start ionizing. Yeah, things start forming hydrogen atom. Okay, so now let's try to review the history a bit. So what we see is that at lambda equal to 10 to the minus 3, this is the era from which the CMB is coming. Okay, so this is the source of CMB. The other observation is that the CMBR is extremely uniform, right? In fact, if you look at the fluctuations in CMBR, okay, the temperature fluctuation, for example, right? It's like 1 in 10 to the 5 because it's extremely uniform. So this basically tells us that universe at a scale of 10 to the minus 3, when lambda was 10 to the minus 3, was extremely uniform. Okay. Now, given that, we can ask, how does the universe today look non-uniform? What small scale, we know that the universe is not uniform. Right? So how did this happen? Right? And what one can argue is that if there are small fluctuations in CMB, right, that basically means that in some regions there is a little more matter than in some other region. But once in some region there is a little more matter, right, because gravity is attractive, it will start pulling matter towards it, and those small perturbations will start growing. So what one can show is that you can explain the current structure of the universe based on the small fluctuations that you see in CMB. In fact, in the early days of CMB, right, when people didn't discover these fluctuations, right, people only knew about the uniform radiation. It was a puzzle that how could a uniform radiation give rise to structure, right? And just from detailed calculation, people say concluded that unless that we need at least 1 in 10 to the 5 fluctuations to explain what we see in the universe today, right? If the fluctuation is less than 1 in 10 to the 5, then there is not enough time for the universe to create all the structure that we are seeing today. And later people found indeed exactly the 1 in 10 to the 5 fluctuations is present in CMB. Okay, so we learned that at universe at lambda equal to 10 to the minus 3 was homogeneous and isotropic. Okay, just from the CMB data. Okay, very homogeneous and isotropic. Now let's look at, suppose this is ours, and let's suppose that we are receiving the CMB from two opposite ends of the sky. This distance in co-moving distance, right? How much is this co-moving distance? Yes. Where subtract what? Yes, the horizon distance. So it's basically the horizon rho h at t naught, say lambda equal to 1. I'll use lambda as the argument, right? Minus rho h at lambda equal to 10 to the minus 3. And twice of this. Right? So this distance, so CMB at 10 to the minus 3 was uniform at least over this distance scale. Maybe it was uniform even before, even more, but that we don't know, right? But we can, this is the maximum distance separation we can see, and we know that over this separation, CMB was uniform. Now the question is, how did it become so uniform, right? I mean, how is it possible for a gas of radiation to become uniform? Now, typically, we know that a gas is uniform, right? If you have a box of gas, the air in this room, for example, has equal density everywhere. Right? That's because equilibrium tells us that the probability of is maximized when there is a uniform distribution. But imagine that you start with a gas which is in one corner, right? It's not uniform, right? You let it go. Eventually, it will become uniform, okay? But it will take time, right? It will take time. And the maximum time, the minimum time that it will take is the travel time for the molecules from one end to the other end, right? If there is a non-uniform density, for example, right, then in order to equilibrate, right, of course, it has to undergo many collisions, but at least it should be possible for them to communicate, right? Otherwise, gas doesn't even know that in one region there is a high density and another region there is low density. Okay? So this is the minimum time required to communicate. Now, at the time of CMB, right, the horizon size was, so this is the separation, and the horizon size at the time of CMB was this, right? By definition, lambda is 10 to the minus 10 times CMB, and so this is the horizon size. Horizon tells us that how far light can propagate from the beginning of time, right? So any communication has to be limited within this range. Right? So if you are saying that it's the thermal equilibrium somehow which made the universe so uniform, right? The thermal equilibrium could make the universe uniform only over a distance scale of this size. Is that clear? Yes, the size of the universe, of course, can be infinite, right? Yeah, size of the universe can be infinite, right? But we don't know that the universe is uniform over the whole its size, right? We only know that the universe is uniform over this distance, right? And we are measuring everything in co-moving distance, so that is comparison is easy, right? Otherwise, you have to multiply by lambda to convert it to that distance. But if you want to use the physical distance at that time, you have to multiply both of these by lambda at that time. Okay, but let's not do that. We just compare co-moving distance. Now, of these two, which one is larger? This is larger, right? And how much larger is it? We can estimate, because let's imagine that it's matter dominated also. Right now, of course, it's cosmological constant dominated, and at the time of CMB, we saw that the universe had already entered the matter dominated era. So in the matter dominated era, the rho grows as lambda to the half. Right? That's what you saw last time. Right? Rho goes as lambda to the half. And so this one will be about 10 to the minus 3 by 2 times rho h at lambda equal to 1. So this is about half of, so this is half times 10 to the minus 3 by 2 times, see in this rho h of lambda equal to 1, I can replace by this, because this is very small compared to this, okay? 10 to the minus 3 by 2. Okay? So rho h 2 rho h at lambda equal to 1 minus rho h at lambda equal to 10 to the minus 3. So this number, I think, is about 1 over 60. So what we learned from this, that is at lambda equal to 10 to the minus 3, the universe was uniform over a distance scale, that is at least 60 times the horizon size at that time. Right? This is the horizon size at that time, right? Which is 1 over 60th of the distance scale over which you know that the universe was uniform, because you can observe. Is this clear? Yeah, so over this separation, we know that the universe is uniform, right? And the horizon size at that time was about 1 over 60 times this distance. Right? The distance over which you know that the universe was uniform, because you can measure the CMB fluctuation, is 60 times the horizon distance at that time, right? But we are saying that thermal equilibrium can equilibrate only over a distance of the horizon distance, right? That's the maximum, right? The question is, how did the universe become uniform, right? So thermal equilibrium cannot help in explaining why the universe becomes so uniform, right? Unless for some reason the initial condition set the universe to be uniform, right? But that's, I mean, who set the initial condition, right? We don't want to invoke magic to explain what we see today, right? So this is what is called the horizon problem. Yeah, that we, at the time of the last scattering, it looks like that the universe somehow was uniform over a much larger scale than what the horizon size would allow. This one, I just multiply half times 2. That is 1, right? So this is okay, right? Half times 2 is okay, right? Because you haven't done anything. And just rho h I am replacing by rho h of lambda equal to 1 minus rho h of lambda equal to 10 to the minus 3, because this is much smaller than this. This is 10 to the minus 3 by 3 by 2 times this, right? So at the order of magnitude, I can just replace it by the difference. Or I could have replaced this by rho h at lambda equal to 1. Okay, there's a reason why I haven't done this, which will become clear later. Is it okay? So the question is, how do we resolve this puzzle? If we want to make these two sides of the same order, okay, or we want to make this side much larger than this, that is okay. Right? That would mean the universe is uniform on a much larger scale than you have observed. But you have to make this at least equal. Right? You cannot live with 1 over 60 times this. Yeah. Yes. Exactly. But the point is that thermal equilibrium can only happen over a scale of the horizon. Right? Because thermal equilibrium requires communication, right? If you have a over-dense region here and under-dense region there, right, they can become uniform by thermal process, right? But that requires that you should be able to the whatever excess is there has to travel there, right? And that can only happen at the speed of light, right? So horizon is the limiting size of that uniformity, right? So the thermal equilibrium or anything that requires communication, right? You start from a non-uniform system and you communicate to make it uniform, can only happen over a horizon scale. Okay? That's the lesson from here. Is it clear? Right? Imagine that you have started with a universe where over 60 times the horizon scale, there's a little over dense region there and under dense region there, right? Eventually they will become uniform, right? But unless the particles from or the energy from the over dense region can travel to the under dense region, right, that will not happen. And it just didn't have enough time for that to happen. Right? So that is a puzzle. Yeah, so what mistake could you have made? Yeah, see, lambda equal to 10 to the minus 3, between here and lambda equal to 10 to the minus 3, the physics is quite well understood, right? It's low energy physics. I mean, you know exactly what could happen in this region. Yes, but we also said that you can divide out the integral into parts, right? And each part contributes, the contribution to rho h from each part can be added, right? So this is basically that, right? That up to horizon light would have traveled here and then from there it's reaching us. Yeah, so this difference is this distance. Yeah, we use the formula for lambda equal to 10 to the minus 3, right? That horizon size is 10 to the goes as lambda to the half. Right? If you replace it by radiation dominated, right, it will not really make much difference. Because it goes as positive part of lambda, right? Lambda is small anyway. Yes. So effectively, so the point is this side of the calculation, right? There is very little scope of making a mistake because these are standard general relativity. we cannot do anything about it. On this side, rho h at lambda equal to 10 to the minus 3. Okay. We assume that the universe was radiation dominated all the way to lambda equal to 0. Right? And we did the calculation based on that. Right? So that is the only place where we could have possibly made a mistake, because lambda, smaller lambda means higher temperature. Right? And at high temperature, we don't know the physics very well. Right? We have our particle accelerators, right, which can go up to temperature of 100 GeV. Right? So you can say up to 100 GeV, you understand what the physics is. Right? And based on that physics, we cannot change anything. Right? Of course, the actual calculation will change, right? But it will only give order 1 effects. Right? The actual calculation will change because, for example, above half MeV, okay, or about MeV, right? Electron positron pair would have been produced by collision of photons, right? Because electron mass is about 0.5 MeV. So then we have to take into account the fact that there is a gas of electrons and positrons, and even at higher energy there will be other elementary particles which have been produced. But those effects, right, are all of order 1, right? Basically, you keep transiting between matter plus radiation and radiation. Okay, because when the electrons are non-relativistic, it looks like matter. When they become relativistic, it becomes radiation. Okay. So that is not going to help with lambda. It will give order 1 corrections to the calculation that you have done, but not very much. Okay. And you can also see that if imagine that something happened between, let's plot lambda here. Let's suppose something happened between lambda 1 and lambda 2. Okay, some small lambda where you don't understand the physics. Typically for matter and radiation, it goes as some positive power, right? Lambda 1 to the alpha. So the net change, the horizon size in this region will be like this. This is the change in delta, the horizon size. So it's from this epoch. Right? While alpha, what we found is a half for the matter, and I don't know, 2/3 for radiation or something. Yeah, 2/3 for radiation, right? So positive parts, and because lambda 1, lambda 2 are already very small, right, this difference cannot really add very much. So the only hope is to try to get a negative power somehow of lambda. If you could get a negative power of lambda, right, then it's possible that at very low temperatures where you don't understand the physics, right, the universe went through a state in which lambda was, the horizon size was growing as negative power of lambda, and so that could add to the horizon size. Is this clear? Yeah. So what I was saying is, suppose between lambda 1 and lambda 2, right? If it's radiation, then it will be, I think, 2/3. Lambda 2 is 2/3 minus lambda 1 to 2/3, right? The horizon size grows as lambda 2 is 2/3 in the radiation dominated era. Okay. For matter dominated era, it goes as half, right? So because lambda 1 and lambda 2 are already very small, right? Because you are looking at a very early scale, right? Because for large lambda, we understand the physics. Right? So if they're already very small, then this change, right, even if something, this physics you don't understand, it cannot add very much to the horizon. Right? So because you are now looking for a factor of 40 or for a factor of 60, right? We have to add the 60 times the current horizon size to the horizon size at 10 to the minus 3. Is that clear? Yeah, so that just saying that, okay, there may be some more elementary particles which are relativistic and hence should be treated as radiation will not help very much in this calculation. What can help is if you get some negative power of lambda, which increases the horizon by a very large number in a small interval of lambda. Exactly. Yeah. You have to change our physics somewhat drastically, right? Just saying that it's matter on a radiation which killed the universe in the early time is not going to help. In fact, it's much less than order 1 effects, because you can see that smaller the lambda, right? This is smaller, right? So if you change the physics at a very early time, it doesn't help very much because lambda is already very small, right? So positive power of lambda will be small. right? So somehow you have to turn this part to negative. Only then you can hope to get some large contribution. So did we see any negative part of lambda anywhere? Sorry, you had a question? Yeah. Exactly. So you have to add something to rho h at lambda equal to 10 to the minus 3. Right? And that will not affect this because here you have a difference, right? So this calculation will not be affected because if you add something to rho h equal to lambda equal to minus 3, the same thing will get added to rho h at lambda equal to 1. By this integral, exactly. So you have to change the integral somehow, right? That integral was based on some understanding of what the universe was in the early times. That when we said that below lambda eq, right, which is 10 to the minus 4, everything was radiation, right? And based on that, so you said that part doesn't really contribute very much, right, to lambda because again because of this positive part. Yeah, that's why I said that most of the contribution to lambda is coming from the matter dominated part of the era between 10 to the minus 4 and 10 to the minus 3, and that gave you this 10 to the minus 3 by 2. So the point is that if we can add something extra to this, right, then we could resolve this puzzle because that something extra will also be added to this. So this difference will not be affected because this difference only tells us how the universe evolved from lambda equal to 10 to the minus 3 to lambda equal to 1. Right? That there is very little scope to change that. Okay, because physics in that regime we understand quite well. Right? Unless you change the laws of general relativity or something, you cannot really do very much. Exactly. Yeah, we know this very well, right? So you have to somehow change this rho h at lambda equal to 10 to the minus 3. Okay, so we need some negative part of lambda, right? In some region where the change in rho involves negative part of lambda. Because negative part of lambda for small lambda could be a large number. So did we see any negative part of lambda in our calculation? Yeah, cosmological constant went as 1 over lambda, right? So let's imagine that in this lambda space, right? We are plotting against lambda. Right? So we have various things. This is the lambda large scattering, right? There is also lambda at equilibrium matter radiation equality. The various things happen, right? And then below this also various things happen once you cross the electron positron threshold, other thresholds and all, right? Because those become relativistic. But imagine that at some point, say lambda 2, all the radiation that was there, all the energy density which was there here, somehow was stored in the form of a cosmological constant. Right? Imagine that here you had all the energy was cosmological constant. How this could happen, we will see later. Okay, but suppose by some magic we could design so that the universe, right, all the energy density at that time was stored in the form of a cosmological constant, and somehow across at lambda 2, it got converted to radiation. Okay, and then it started evolving as we see it. Exactly. No radiation, no matter. No, it will not be sharp bound, right? So let's take sharp right now, right? Later on, when you understand the physics, how it happened, we will see that it's not a sharp bound. Right? But let's, for the sake of argument, let's suppose it's a sharp bound, right? At lambda 2, it was something else, and maybe it was like this till lambda 1. Okay, before that, we don't know what happened, right? What was the state. Yes, yeah, exactly. Well, I mean, the argument is that we need negative power of lambda, and we have seen also already in our analysis yesterday that in the cosmological constant dominated area, lambda, the horizon size grows as negative power of lambda. Right? It was 1 over lambda 2 minus 1 over lambda 1 minus 1 over lambda. Right? That's what we had seen. No, it doesn't, because it will if alpha is negative, right, and if lambda, then you can make it get a large number by making lambda 1 to sufficiently small, right? Lambda for lambda equal to negative, this will also switch. It will be lambda 1 to the minus something minus lambda 2 to the minus something. Yeah, it's puzzling, right? We learned that the cosmological constant doesn't exchange energy, right? We'll come back to that, right? Let's suppose that by some magic it was not true, right? That all the energy density was in the form of cosmological constant. Right? Now, clearly, that cosmological constant would have been much larger than what we observe today, right? So, what you're talking about is not today's cosmological constant, right? Because as you go in the past, right, the radiation energy density is growing like 1 over lambda to the 4. Right? And you're talking about a very, very small lambda, right? Where the temperature is above 100 GeV. So, but whatever that energy density was, let's imagine that it was stored in the form of a cosmological constant. Okay, between lambda 1 and lambda 2. So in this region, let's just solve this equation again, right? Even though we have done it once. So we have the equation lambda dot over lambda square is 8 pi g over 3. Let me call this rho tilde lambda. Okay. This is the new cosmological constant. Cosmological constant in the past. Okay. Yeah. This all this is happening. Lambda LS is the same. The last scattering surface, right? That's what the surface that lambda equal to 10 to the minus 3 is what is called the last scattering, where the photons that we are seeing scattered last from that surface. Right? Then there is lambda equal to 10 to the minus 4, where the matter and radiation energy density becomes equal. Right? And then a lot more things happen here, right? As I said, once you cross the electron-positron threshold, the electron-positron system has to be thought of as a gas, a relativistic gas, right? Massless particles, because the energy is much larger than the masses of electrons and positrons. So a lot of things happen, but those are all small effects, right? As far as the horizon is concerned. Okay, because already lambda has become very, very small. So the change in the horizon size in those epochs is very small. But in this case, we can see that lambda will grow exponentially, right? So lambda is some constant, then the exponential but what we really want is the horizon size, low h. So this was basically d lambda over lambda, right? That's what you had seen. No, not d lambda over lambda. So let me do this. Yeah. So we had ds square equal to minus dt square plus lambda square d rho square, right? We are ignoring all the angular directions, okay? Because yes. But when I say it's cosmological constant, we saw that cosmological constant is independent of time, right? By energy momentum conservation, cosmological constant is a constant. So when I declare that it's a cosmological constant, right, then by definition it's independent of lambda. Right? The energy, the T mu nu is proportional to rho tilde lambda times G mu nu, right? Whatever the G mu nu was at that time. Okay, you can ask, I mean, how can you get a cosmological constant, right? On the one hand, it's changing, right, from cosmological constant to radiation. So clearly here the energy density is, the equation of state is changing, but here you are seeing that it remains fixed, right? So how that happens, we will see in a little later, right? But suppose it happens, okay, then what will happen, right? So d rho, so this is equal to 0. So d rho is dt over lambda t. But from this we get dt equal to okay, so this will be square root of 3 over 8 pi g rho lambda times dt over lambda t square. This is correct, right? Okay, I just used this equation to write dt as this, right, and then substituted here to write this as sorry, this is d lambda. D lambda. We converted dt in terms of d lambda. Okay, so this tells us a change. So delta rho h, or maybe I write explicitly rho h at lambda 2 minus rho h at lambda 1. No, because between these we are saying it's cosmological constant. So this difference is square root of 3 over 8 pi g rho tilde lambda is 1 over lambda 1, because d lambda over lambda square integral is minus 1 over lambda, right? And we are integrating from lambda 1 to lambda 2, so that's this. Is this clear? And now we see that doesn't matter how small lambda 2 is. Right? Let's imagine that it happened very early in the universe. We have a very small value of lambda 2. We can always take lambda 1 to be sufficiently small to make this as large as you want. Right? So the universe somehow was dominated by cosmological constant in the early time. We can add to the horizon size. Is this clear? So physically what is happening, okay, is the following, that in this time it's an exponential expansion, right? Lambda grows exponentially as a function of time. So that's a rapid growth, and also this is large, right? Because rho tilde lambda is the energy density at that time, right? We said that all the radiation energy density was actually cosmological constant. Okay? So there is a very rapid expansion in the past, right, which is much more rapid than what we would have expected in a radiation dominated universe, right? Because in the radiation dominated universe, the growth is only power law. In a cosmological constant dominated universe, it's an exponential growth, right? So it expanded very rapidly. Right? So what we think of as 2 points which are not very close in the past, so that they are within each other's horizon, right, actually was very close in the past, right, because the 2 points have been separated by this rapid expansion. Right? So if for example, those 2 points, okay, the temperature had already been uniformized earlier, right, before this thing started. Then the expansion of the universe, right, this rapid expansion would have pulled them far apart, right? And it would look, if you didn't know about this rapid expansion, right, you would conclude that they could never be in equilibrium because they are very far. They are always outside each other's horizon, right? But actually they are inside each other's horizon, right? This rapid expansion which is fooling us, right, if we don't know about this. Lambda, don't forget about temperature, lambda. Lambda is there, right? We are not changing the FRW metric, right? We are still taking this metric. Don't define, right? I mean, where do I use temperature here? Whatever, all fluctuations would have uniformized. Energy density would have been uniformized. Right? Whatever could possibly change from one place to another, right? We are saying let's assume that it has uniformized. Yeah, see, before this, suppose it was before this, it was again already guessed, right? There would have been notion of temperature, right? And that some thermal equilibrium might have equilibrated them. Okay, then this sudden expansion happened, right? 2 points which are close by got pulled apart very far, and then later on it looked like as if they are very far and they could never be inside each other's horizon. So how come they are uniform? So this mechanism is what is called inflation. That you add to the history of the universe some rapid expansion in the past, right, which somehow uniformizes far away points. Okay, points which look far away from us today. Is this clear? That mathematically it should be clear, right? Mathematically it just says that this number can be made as large as you want by taking lambda 1 to be small. Right? Physically, what is happening is this fact that because of this rapid expansion, right, if we didn't know about the rapid expansion, we would have concluded that they can never be inside each other's horizon. Right? Because if the universe continued to be radiation dominated in the past, then the light couldn't travel very far. Right? Here what's happening is the light doesn't travel very far, but the expansion of the universe stretches it out. Yes, indeed. After that, matter dominated, right? Then the last scattering surface is when the photons decoupled from, when the scattering of the photons stopped. Right? This is the image we are seeing today. That if we could observe gravitational waves from the early universe, we could have determined for the universe how, to what extent the universe was uniform, right? Because you could have gotten signal from even farther distances, but not very farther distance, right? Because after all, the horizon limits us. Why? It does, because if you start with a uniform initial condition, the uniform initial condition is being fixed by this expansion, right? Here it was not uniform. Here the uniformity was only within the horizon size at that time. Okay. Now because of this expansion, right, the horizon got this thing got added, right? So within the horizon size there, right, today would have been much larger horizon size because this got added, right? And the uniformity would have occurred across that. Near lambda 1. Lambda 1. No. We are providing only uniform initial condition over distances within the horizon scale.
So that was going to my next question. So this cosmology is a very bizarre. How, for example, for matter, I can imagine how it.
I have not explained how the cosmological constant comes. That question you have to ask for once I explain how the cosmological constant comes, right? Right now we are saying, let's suppose there is a cosmological constant. Okay? But we are not assuming that does magic, right? We are only saying that adds to the horizon. It's just general relativity, right? Here, right, we are only saying that let's suppose that there is a uniformity over the horizon scale at this point, right? This is acceptable, right? The uniformity in horizon scale. Now we are saying that the horizon gets added to the horizon scale, right? Which means if 2 points are far within each other's horizon, they will be far apart now. If they are uniform to begin with, right, they will still be uniform at the end of it, right? Because the co-moving the same co-moving thing is expanding, right?
So my question was like, when it is resonant, the argument usually goes with the permanent.
Yes.
How does it come?
As long as there is enough interaction, right? What one can show is that as long as the interaction strength is the interaction rate is larger than the expansion rate, it will thermalize.
No, but what are the interactions?
Standard model interactions, right? W bosons decay into other things collide to form W bosons. Any kind of interaction is fine, right? Elementary particle interactions.
There is matter during that.
Those are all treated as radiation because at that high temperature, right? Those are all radiation, but unlike photons, which don't interact very much with each other, photons still scatter. 2 photons can scatter into 2 photons. Oh no, yeah, fine. But as long as here the energy density was very uniform. How did it vanish? Oh, yeah, it vanished because this 1 over the rapid expansion, right? Also was 1 over lambda to the 4, right? So it goes both ways. That if you go in the past, right, the rapid expansion will make it larger, right? But if you start with the 1 over lambda to, if you start with some radiation density, and the universe starts expanding, right, cosmological constant always dominates at the end, right? So as long as this is large enough, the cosmological constant will dominate. Okay. But we'll see. I mean, once we describe how the cosmological constant comes, maybe things will become a little clearer. Okay. No, we don't know because you don't understand the physics there, right? So lambda 1 could go as close to 0 as possible, as you want. All of those are here after this. So for that, I have to explain what the cosmological constant is, right? Only then you will know if there are interactions. Okay, so let me explain how it should happen. Okay, what this is saying is that if somehow in this region, radiation, all the energy density was in the cosmological constant, okay, then we could solve the horizon problem, right? Because the actual horizon size at the last scattering surface was much larger than what we would have thought naively, okay, because it just gets added. So the horizon problem is solved because the horizon size at that time would have been larger. Yes. Yes, yes, it will. It will. Yes.
I thought the value that we talked about size of the is great times 40. So that get affected, that is correlation.
That get affected, but that is actually not relevant, right? Because I remember I told you that how are you going to use the age, right? Then no rock should be older than the age of the universe, right? No rock existed before the last scattering surface anyway. right? So what is relevant for us, right, is not the whole age of the universe or the whole horizon, but say age between last scattering and today. That is good enough, right? Because no rocks existed before that anyway, right? So lambda is very, yeah, lambda, because lambda is always increasing. T correction need not be very small, because you see, when you have something like this, right, to go to lambda equal to 0, you can take T all the way to minus infinity, right? So in principle, it could have started at minus infinity. Say we fixed our origin of time, thinking it's radiation dominated all through, right? But if the cosmological constant dominated era lasted for infinite time, right, then lambda equal to 0 would have been reached at infinite past. But that addition to the age, right, is not really relevant, because that time we cannot compare with anything else. Right? So for all practical purpose, what we call the age of the universe today, right, you can think of just as the time between the last scattering surface and today. Yeah, or maybe if you want to go a little more, between, say, when the electron positron period was, went non-relativistic, from that to today. You don't have to go much before that.
When we say about this time will be going, the cosmological constant will be important and dominating, and everything will become sort of separated except the bond system.
Yes.
So in this kind of a case, something was there initially. After this kind of inflation, there is like, seems like there is nothing left to.
True. True. Except the cosmological constant. Right? So that somehow has to create radiation. See, that's the step. Right? Cosmological constant has to become radiation.
Okay, then again everything will start from cosmological constant.
Exactly. Right? So we have not so far understood how the cosmological constant can possibly become radiation, right? Because cosmological constant is supposed to be constant. If this was cosmological constant, it would have remained constant, right? So that is the thing we have to understand, right? That how come the cosmological constant become radiation? Yeah, in the far future, it goes back to cosmological constant again. Well, changing a lot of things, because this cosmological constant is much, much larger than what we see today, right? No. Yeah, rho lambda tilde will be fixed, because suppose you assume that it's radiation dominated all the way here, right? Then we can calculate what is rho at this point by evolving backwards, right? Once you fix lambda 2, you know what rho here is, because you just follow the radiation dominated era, the 1 over lambda 4 to the 4, that formula, right? That would have been the cosmological constant. Yeah. Which 3? No, rho is not fixed. Rho is not free. Because once you have fixed lambda 2, right, and you have said that after this everything was radiation, right, we know what rho was there. Okay, so rho is not free that way. So where that. Okay, so let me now try to explain the dynamical model, how it could happen, right? That how can we get a cosmological constant certainly? So we consider a scalar field. Okay, where V phi is some function of phi. right, which is normally called the potential. I'll not, I'll describe what kind of A5 you should choose later. Okay, let's imagine that you have a scalar field like this, coupled to gravity. Now, if you remember, we defined the energy momentum tensor, right? Delta S is half integral d4x let me call this phi. This is the energy momentum tensor of the scalar field, and you have to add other things to it. Okay, the radiation, etc. Is it clear? So using this, we can calculate T phi. This is a simple exercise. You just have to take this action and vary the metric. Right? This is G inverse, right? So you have to use that formula. Delta of G inverse is minus G inverse delta G inverse. And you will get T mu nu. Now suppose for some reason phi varies slowly in space and time. The derivative of phi is small. Okay, so if then we see that T phi mu nu right, because all these terms are small, right? We get minus V phi G mu nu. So this looks like a cosmological constant. So V phi appears like a cosmological constant because that's the way the energy density of the cosmological constant was, right? Because it's proportional to G mu nu, and its T00 is V phi times G00, right? Positive. So this is like a cosmological because this behaves like a cosmological constant. So scalar field whose potential is not zero, right, can act as a source which looks like a cosmological constant. Is this clear? Now we have to choose the potential appropriately because we have assumed that these are small, but okay, I mean you have to make sure that these are small, right? Because if you start from some value of the phi, right, then the phi also has its own equation of motion. Right? It will start moving. Right? So the derivative of phi will not be zero anymore. So the potential that one chooses is something which may have something, some slope here, but then a range over which phi is almost flat. Okay, but there is a small slope on this direction, so it's decreasing and then like this. Well, it touches the zero almost, except that rho lambda that we see today. Right? You can think of that as this. Because today we have some cosmological constant, right? So we should leave out some, but that is really negligible compared to the kind of energy scale you are talking about. Right? So I mean, if you want to really draw it, it should touch 0. Right? If you not, so that small cosmological constant in this scale. So what happens is, suppose phi is somewhere here. Okay, you can write down the equation of motion for phi. Okay, take G mu nu to be the FRW form, and you can easily convince yourself that if the slope is small here, right, that means V prime phi is small. Right, what will happen is that phi will move, roll down, but it will be very, very slow. Okay. So during this roll of phi over the slope, the energy momentum tensor will behave almost like a cosmological constant. And when it behaves almost like a cosmological constant, right, then even if there are some spatial derivative to begin with, right, suppose there are some small fluctuation of phi in the space direction, this rapid expansion, okay, will basically erase that, because the close by points, right, will get separated out. Right? So if there is a fluctuation over some distance scale, right, that distance becomes so large, right, that you think of phi as a uniform. Right? So the spatial derivatives get wiped out. The time derivative doesn't quite get wiped out. There is a small contribution because phi is rolling down. Okay? But that's a slow roll. Okay? That's what you are doing, right? Because that's why it's a cosmological constant. Because it appears on the right hand side of Einstein's equation, but it appears as a cosmological constant, right? Okay, so it's self-consistent that if the scalar field is slow rolling, right, it will modify the Einstein's equation, but it will be like a cosmological constant, right? So the universe has an FRW form, except that the expansion is exponential, right? And that exponential expansion basically adds to the horizon. Right? So if the scalar field was not uniform over some distance scales outside the horizon, right? Because the horizon size is increasing, that the non-uniformity, right, gets diluted. Right? That's the physics. So the close by you expect things to be uniform, right? Because otherwise the gradient, you don't want scalar field to have large gradients, right? Because that costs energy. So close by you would have expected them to be uniform anyway, right? Just from energy minimization, and that close by points become very far away. So it looks like that the scalar field becomes uniform over a larger scale. Right? So that is the physical, that's the physics, but the mathematical statement is that the horizon size gets increased. This one, yeah. So the early universe scalar field might have rolled from here, right? It might have been somewhere here, but you are talking about the part where it start here, right? Because you only need some region where there is a rapid expansion, right? In the past, it could have been something else. So in this region, what happens is that the scalar field energy is there, right, which is V phi. Anything else that was there to begin with, say radiation, matter, etc., would have gotten so diluted that they just don't contribute, right? Because as you saw, the cosmological constant remains constant, but the matter, for example, falls off as 1 over lambda cube. The radiation falls off as 1 over lambda to the 4, right? And the kind of numbers that one needs, right, for solving the horizon problem is when this lambda expands about at least e to the 60 times. Okay, so you think of if lambda increases by e to the 60, right, it's exponential. So e to the 60 is a large number, but in terms of time, it's not that large, right? It's 60 times the natural time scale. So this rapid expansion basically dilutes matter by e to the minus 180, right? Dilutes radiation by e to the minus 240. Okay, so that basically is all gone. All the energy density is in the phi field. And then what happens is here, the phi field starts rapid oscillation. That is what we had called lambda 2 earlier, right? Once it starts rapid oscillation, right, then what one can show that basically it gets converted to other forms of energy. Okay, eventually mostly radiation. So that's the physics, right? That's the way inflation tries to resolve this problem, that at this point, right, because of this rapid oscillation, you just see radiation after this. Okay, but this is not abrupt, right? That was the question. So lambda 2 is short, right? In physics, nothing is short, right? This takes time, right? At this time, it will be a mixture of everything, right? The actual energy density, right, will be given by this whole thing. Okay, but eventually it will come to thermal equilibrium. Okay, and it will become, this thing will convert to radiation, and from there on we evolve by the standard equations that we have seen so far. Oh, we are far away. I mean, it has already converted everything to radiation. Oh, that is because here phi has settled down here. Okay, so this height shouldn't be exactly 0, but it should be equal to our cosmological constant. Yes.
Let's say instead of this one,
Hmm.
it has some it can be equal and I think like here they're choosing a classical solution, right? Let's say now choose one of the standard. So the phi field will be stuck there.
Yes.
And that will also explain our cosmological constant.
Our cosmological constant, but not cosmological constant in the past. You see, to explain the cosmological constant in the past, right, you need a flat, large potential, right? It has to remain for a while, so it has to be flat. But it shouldn't remain there because today's cosmological constant would have been that, right? So that's why you need this part. Right? In any case, I mean, you know that the universe was radiation dominated earlier, right? So we have to somehow convert from here to radiation dominated area. Is this phi equivalent to lambda? No, phi is a function of lambda, right? You can write phi as a function of time, but time and lambda can be exchanged, right? So phi you can think of as a function of lambda, but all this happened at very small lambda.
One more explain how to. I understand that this the constant part corresponds to the inflation.
How do you write draw? Oh, I just drew it. Meaning the point is we need this kind of potential to solve the problem, right? See, if it was just flat, inflation would never end, right? Okay, so that's why you need this kind of potential. So, okay, this is an idealization, right? People have tried various other kinds of potential, okay? But the main point is that we need some part where it looks like a cosmological constant, and then other parts it becomes radiation. Okay, it's not that only this kind of shape will work, okay? But there should be some region where there what people call slow roll, right? Where the energy density will change slowly, okay, so that it effectively behaves like a cosmological constant. Well, this is a side, I just drew it. Here, what happened, it really doesn't matter, right? Because whatever happened here, right, it gets completely wiped out by this, because this expansion is t to the 60 at least, right? So that kind of expansion basically wipes out whatever fluctuations, whatever was physics were here, right? It basically creates a cold uniform universe, okay? And there, from there, you transit into this region. Exactly. Phi will be oscillating, and eventually it will get converted to radiation. The field goes like this, like harmonic oscillator, right? It will be damped because the phi will, I mean, it's quantum mechanics, right? It's quantum theory. So phi, I mean, if you quantize a scalar field around this minimum, right, you'll get some massive particles. But those massive particles are typically unstable because phi will have interaction with other fields also, right? So what will happen is that you can think of, at this stage, you can think of this as a lot of massive phi particles are being created, right? But those phi particles start decaying into usual radiation, right? And that's how radiation is created. So this part is what is called reheating, right? That's a, subject by itself, right? How did inflation end? Okay, and there are various models. In some model, the reheating happens very fast, right? In some model, it stretches out over several scales of lambda. Okay, and those models have different consequences. Yeah. Yeah. Well, except that there is no, in this case, the energy, unlike in radiation dormitory reduction, smaller lambda means the higher energy density, right? In this region, energy density remains constant. It's cosmological constant dominated, right? So here again, it starts increasing if it was radiation there. Yes.
So this is sort of modeling the overall content. What is the radiation? This is
No. This is only the phi content. There are also you have to add the T mu for other things, right?
yeah, but if everything coming from the cosmological,
Yes.
the initial part, this phi is representing some cosmological constant. Then so there is a harmonic oscillation and some of like massive particles.
Yes.
And then these massive particles will give it.
Yes.
So this is like our idea was this phi represents the cosmological
Early universe.
in the early.
Yes.
Okay. So from that onwards, once this oscillator potential, and from that onwards, it is the combined of cosmological constant plus radiation.
Exactly. Okay, that's cosmological constant basically has died down here, right? Okay, this is this height is like today's cosmological constant. So that is a negligible compared to the energy density there.
So I'm thinking whatever the energy constant that you
Because you have to couple other terms like the electromagnetic part I have not written, the coupling of phi to electromagnetic part I have not written, right? So all of those will contribute
all of those will contribute
to T mu
the
nu.
inflation is
Exactly, right?
inflation is over.
Exactly. But during inflation, right, all those die out because, as I said, all radiation, matter, etc., get diluted, right? So at this stage, all the energy density is coming only from phi.
So once this cosmological constant will it automatically give all those
No, it doesn't. I mean, you have to add the term in the Lagrangian. If you declare that this is our universe, right? This is our theory, then there is a photon. So how will you produce radiation? Right? You have to add the full Lagrangian to this at least the standard model Lagrangian, which you know. Right? And you also have to have a way to couple phi to the standard model fields. Right? Because the phi particle, otherwise the phi particle will just remain as massive phi particles, right? The universe will remain matter dominated and there will be no radiation. So you have to have a way to couple phi particle to also the standard model field so that ultimately the energy gets transferred to the standard model fields. Right? Phi doesn't carry any energy because phi becomes massive particle, right? And if they couple to standard model fields, because basically phi decays at low energy.
So what are these couplings like? Are these derived?
That depends on your model, right? There are various models of inflation which has various kinds of coupling.
But it is not derived. I didn't check that. If it is phi,
Yes.
Lagrangian that term won't be ignored, right? Phi
Yeah,
equals-
but that basically, if phi is there and if it's like a constant, right? That basically means maybe it will produce a mass for those. Right? Those will be regarded as very heavy particle, but they are just not there in the universe, right? So there may be very massive particle in the universe, but if they're not present, suppose there are some density of those massive particles, right? They'll just get completely diluted during this expansion.
the dilution that you told, like the power very small.
Exactly. Because lambda lambda grows as exponential time, right? Okay. So this over this distance, right? Lambda is supposed to grow at least 10 to the 60 times. Exactly. Yeah. Coupling will basically tell you what the masses of those particles were at that time, right? But because of the rapid expansion, even though some of those particles are present, right, they are just diluted away. But yes.
There is a when the phi is oscillating.
No, so that, then it's not cost. Then there's the energy momentum tensor. You have to just look at the energy momentum tensor, right?
Till that constant point, there is some inflection.
Exactly.
Cosmological constant is.
Yeah. After that, you shouldn't talk about cosmological constant. You just talk about the whole energy momentum tensor. You can still use this to evolve, right? The Einstein's equation.
So what is this del V phi?
Exactly. Basically, it's a time derivative which will come, right? Because if everything has been uniformized in the space direction, right? Basically, it's a time derivative which will contribute, right? But then it's not separately cosmological constant, matter, radiation. It's just this, right? As long as you can use classical physics, right? But eventually, when you think of these as phi as particles, right, then you have to use quantum physics because phi will have to decay into all other fields, all other particles. Yes. Yeah, so the classical description is for this part, right? Here you really need some quantum information, right? Because this oscillating phi eventually will have to decay to other particles. Well, if we can produce energies of that kind, you may be able to detect, right? Just in accelerators. But the point is there is something that we can detect, okay? And that is the following, that see this expansion, it solves the horizon problem, but it gives the opposite problem, that if it made the universe so uniform, right? Then where is this 1 in 10 to the 5 fluctuation coming from? Right? Now we have to explain why the universe is not completely uniform.
That concept last case is in between lambda q and lambda last case is something.
Yeah, let me put it this way, that if you have made the thing very uniform, right? It is true that there is thermal fluctuation, right? In between, so which could give rise to those fluctuations. But just like thermal fluctuation cannot produce non-uniformity, it also cannot produce non-uniformity outside the horizon scale. Right? Imagine the average densities were equal everywhere to begin with, right? Then thermal fluctuation starts. Things, start energy densities don't remain completely uniform, they just start fluctuating, right? Because particles are moving here and there. But they can only move up to the horizon scale, right? So if you do the averaging outside the horizon scale, you should see no non-uniformity. Yeah, but the question is that if you have 10 to the 60 expansion, right? Then everything will be 0 at the end, right? There should be no fluctuation at all. Okay. So here the way it happens is that what one can show is that during this rolling, right? Classically, nothing is happening. Okay. But once you take into account the effect of quantum field theory, okay, quantum fields fluctuate in this background. Okay, basically gravity plus phi, right? You have to quantize gravity plus phi in this background. That gives rise to quantum fluctuations. Okay? And those quantum fluctuations eventually get converted to classical fluctuations that you see today. Right? So in that sense, the CMB spectrum that we are seeing, right? This is capturing information about phi. Okay, the quantum fluctuations of phi during inflation. Okay? That's what we are seeing today. And us, because CMBR is the reason why we are there, right? Because unless there are fluctuations and stars and galaxies formed, right? It will remain completely uniform. For that, you have to wait for the next course. That you cannot explain in one lecture. Okay, so the final thing that I'll say, okay, is that the explanation of why this k over a0 square is very small, right? So somehow k over a0 square is small today, and it was also small in the early universe, right? Because you know that it's compared to the radiation energy density, it should have been even smaller. So the point is, imagine that we here when the inflation started, right? The two terms are of the same order, right? What are the two terms? One is the energy density that is coming from the cosmological constant, right? That 8 pi g over 3 rho lambda, right? This was one term, and the other term was k over a naught square lambda square. Right? If you look at Einstein's equation, right, these appear on the right, left hand side, these appear on the right hand side. Okay. And then naturally, you would expect that, okay, if there are several terms in the equation, the natural condition is the initial condition will set them to be of the same order. Right? So imagine they are of the same order. But this is lambda 1. By the time you have gone here, right, this would have become lambda 2. This would have remained 8 pi g over 3 rho lambda. Right? But this would become k over a0 square lambda 2 square, right? Because it goes as k over a0 square lambda. Lambda 2, we have said, is at least 10 to the 60 times lambda 1. Right? So at the end of inflation, right, this term would be much, much smaller than the cosmological constant. Right? This gets converted to radiation. Right? So which means that after the cosmological constant has gotten converted to radiation, the curvature term will be much smaller than radiation energy density. And that is what has propagated today, right? So today, for example, that ratio would have increased because radiation energy density falls as 1 over lambda square, whereas the cosmological constant, whereas this curvature falls as 1 over lambda square. Right? Lambda to the 4 versus lambda square. But nevertheless, if we had a gain of 10 to the 60 from the beginning, right, then this power law expansions, right, 1 over lambda square is not going to compensate for that. Right? So that is the explanation of why k over a0 square is so small. Because inflation essentially solves many things at one go, right? These are the two of the things that it can address, right? One is that why is the universe uniform over so larger scales, right? Then why is the curvature small? Okay? And of course the production of fluctuations, right? It not only tells why the universe is uniform over larger scale, but also tells us why it's not completely uniform. So basically what inflation does is it tells us that what happens before this is irrelevant because everything gets uniformized during this rolling, and then the quantum fluctuations create everything that follows. Oh, if the scalar field is like this, see, nobody knows anything, right? If the scalar field, I mean, if the scalar field potential was like this, right? Then once the scalar field starts rolling and reaches here, it has to roll down, right? In fact, I think the homework problem, the last homework problem basically involves the scalar field coupled to gravity, right? Where I think this part was given as a straight line, uniform slope, right? And then suddenly it falls. Yeah, so it's basically the depends on the shape of the scalar field when the inflation will end. Okay, I think I'll stop here. So no direct observational evidence, right? The fact that this horizon problem, yeah, so these are all indirect, right? There's no observational evidence, right? Or the microwave, the fluctuations that we see 1 in 10 to the 5, right? In inflation, they are produced by quantum fluctuations, right? But there's certainly no direct observational evidence. Pardon? No, I think gravitational waves will also be produced during this part at quantum fluctuation that they may become classical gravitational waves. The point is here, all massless fields fluctuate, right? So gravity also fluctuates, and the scalar field fluctuates. What we see in the sky today are consistent with the scalar field fluctuation. Right? You have not seen the gravitational field fluctuation effects, right, which are called the tensor perturbations. Right? That is something that people are looking for. And the reason that that gives an important information is because if we know the amplitude of the gravitational field fluctuation, right, that contains information about the scale at which inflation took place. Right? What was the value of this height? What was the height of this potential? Yes. Yeah, as long as it's acceptable to everybody. 13th is fine. Yeah, so next class we have to decide, because the only one topic is left, which is the tetrad or Feuerbach formulation. Okay. Now the question is, how many of you know about Dirac equation? Dirac equation, I think the post BSc students don't know, right? So what I'll do, I think Godwin wants to give those lectures, right? I'll plan with Godwin. Okay. It will not be part of the syllabus, because and if you are only interested in classical gravity, right, you don't really need it. Okay. But if you are planning to work in quantum aspects of gravity, right, then you should definitely attend, even if you haven't done the Dirac equation, right? It is necessary that you attend, because you cannot couple fermions to gravity without going through this Feuerbach formulation. Okay, so those lectures will be in the, not next week, there will be no lectures, right? The week after. Yeah, that will be the end. So I'll talk to Godwin and then fix this. So, okay, let me count again. So how many people have not seen Dirac equation at all? Okay, 1, 2, 3, 4. Okay, 5. Okay. Okay, so we'll see what to do. Right? I'll talk to Godwin, and maybe we'll have one lecture on Dirac equation and then 2 lectures on Feuerbach. Right? Pardon? No, I think cosmology is more or less the end of this course. Right? And the next semester we'll have more detail.